Hello everyone, welcome to this class. Over the next 45 minutes I will give an overview of graph theory concepts applied to brain connectivity. I'm Giovanni Volpe, I work at the University of Gothenburg, and during the last 10 years I've been working with brain connectivity applied to the brain, developing the software graph, which you will see during the tutorials. So let's start with a riddle. So this riddle was very popular a few centuries ago and in the city of Königsberg in Central Europe, and the riddle goes as follows. So you see here a map of Königsberg, and the question is, you see that there is a river and various islands and several bridges. These ones highlighted in orange are bridges between these islands. The riddle is, how can I go, let's say I'm in this island to start with, how can I go around all the islands, crossing all the bridges once and only once, and come back to this island? A very popular riddle at the time, and people were actually trying to solve it by walking around the city of Königsberg, which arguably is a pretty healthy activity. Anyway, I will now leave you some moments to think about this riddle. Please pause the video, think about your solution, and when you're ready, come back. In the meantime, I will go and get myself a cup of coffee. Okay, so I hope you have found a solution. Maybe not. In any case, you might have noticed that there are lots of details here, and this makes finding a solution pretty difficult. So, too many details. Maybe we should focus only on some of the properties of this system. And one way of doing that is looking at this city as a series of land masses and bridges. So that's really everything we really need to know. We don't really care about the exact buildings and churches and the names of the streets. So we see that we have 4 land masses. Let's call them A, B, C, and D, and 7 bridges between them. So now we are left with this much simpler system. In fact, we can even go one step further and simplify even further, making it a graph theory problem where we have only 4 nodes, A, B, C, D, and connections between them. So 2 connections between A and B, 1 connection between A and C, 2 connections between A and D, 1 connection between B and C, and 1 connection between C and D. This is essentially the transformation of the problem that Eulero did, and that permitted him to find a solution to the problem. Why? Because when we transform the map of the city of Königsberg into a graph, we immediately see that if we want to go around all the nodes of the graph and come back to the same node, well, we'll need to go in and out of the same node a certain number of times. This practically means that I will need to have everywhere an even number of bridges. But you see that C has only 3 bridges, which means I cannot go in and out and a certain number of times. I can go, for example, if I start in C, I can go out once, I can come back in once, and then I go out again, but then I cannot go back through one of the same bridges. So Euler found the solution in 1735, and the solution was, it's impossible. In order to make it possible, well, you will need at the very least to build another bridge between C and, well, you will need to make all the bridges, number of bridges between every island even. And with this discovery, Euler managed to create so Euler in 1735 discovered the solution, which is it's impossible because the islands don't have an even number of ridges. This is a very important work of Euler, and a work that actually demonstrated once for, well, a work that gave birth to two fields, huge fields of mathematics, topology and graph theory. That's a pretty important work. So, let's now focus on graph theory concepts. First of all, what is a graph? Then, so let's now have a look at the outline of the rest of the lecture, which will go through simple questions. First of all, what is a graph? Then how we can build a graph given structural data or functional brain data. And finally, how we can then measure something on this graph and how we can compare different graphs. So let's start with the definition of what is a graph. A graph is essentially an object which includes nodes and connections. So there are various nodes that are connected by edges. Just to give examples of graphs that you for sure know, you can think of a social network where the nodes can be the various individuals and the connections are, for example, the friendships on Facebook. One can think of a food network where the nodes represented by different species and the connections, the edges, are who it's who. Notice that in this case the connections are directed differently from friendships that are typically bidirectional. One can think about a very interesting case, which is a disease spread network, where you have in the network individuals or cities, and the connection are represented from which city spreads the disease to which other cities. This is a very interesting work from 10 years ago maybe, in which they studied how SARS was spreading through the network of connections given by the various airports. And finally, we can also think of the brain, which is also a network where the various nodes are represented by the brain regions, and the connections are, we will see that in a moment actually. So let's now see what kinds of graphs we are typically interested in. First of all, we can think of a graph. For example, let's think of an individual A, which might be connected with other individuals, B, C, D, E. And we can imagine that A is connected to all these individuals. And then B and C are connected back to A. And B is also connected to D and C. And D and E are bidirectionally connected. What you see here, it's a network which is directed. So here we have a directed graph. For example, this might be the network of people that say that like other people. So if you make a list, not necessarily if A likes B, not necessarily B must like A in return. So it's a directed graph. This is the same graph, but now we can say, ask each individual, how much do you like the other individuals? So we have a weight. For example, A can say he likes 8B, but B might like 1A, and so on. So we have a distinction between a binary graph, where we either have or not have connections, and a weighted graph, where we have a weight associated to each connection. Then we can make an undirected graph, where we just have a connection between individuals and a weight. You see that this graph, this undirected weighted graph, is obtained from this directed weighted graph, taking as value of the connection between two individuals the average between the connection, the two directed connections between these individuals. For example, D is connected to E with the weight 8, and E is connected to D with weight 10. In average, it's 9. So the undirected weight between D and E is 9. Finally, we can disregard the weights, and we will have an undirected binary graph, where we have just the connection. So in this case, which individual is connected with whom. One way to represent the graphs is by using matrices. So here you will see that it's a very powerful way. This is called adjacency matrix. And you see that in this matrix we have the individuals both on the in each column and in each row, A, B, C, D, E. So then the question is A connected with each one of these individuals? So is A connected with A? Of course not, because it doesn't have a self-connection, which could be possible in principle. But A is connected with B, and with C, and with D, and with E, because you see that A has direct connection from A to B, from A to C, from A to D, E to A to D. So we have all of these. And then the question is B connected with A? Yes. Is B connected with C? Yes. Is B connected with D? Yes. Is B connected with E? No. Then C is connected with A, and that's it. D is connected with E, and that's it. And E is connected with D, and that's it. So you see, this is the directed binary graph corresponding to this graph. This is its corresponding adjacency matrix. We can do the same with a weighted version of the adjacency matrix, where we just fill in, instead of black and white, also the values. In this case, all the black cells are assumed to be 0. Then we can take the undirected version, which how will it look like? Well, the point is this: in an undirected graph, if A is connected to B, also B is connected to A, so it will always be, well, perfectly symmetric. And also the weights are symmetric. That's a signature of the fact that this is undirected. And finally, we can have the undirected binary version, in which we just disregard the weights. So we have a matrix where the cells are either 0, the black cells, or 1, the white cells. So also in this case it's symmetric, because also this one is an undirected graph. So here you see the most common kinds of graph that you will encounter in a graph theoretical analysis applied to brain connectivity. Now, this tells you what kind of matrices we can have, but the question is, how do we get from actual brain data about subjects to the brain connectivity? So we have seen how we can, we have seen what kind of adjacency matrix we can consider typically. Now the question is how we can construct this adjacency matrix starting from actual data. So first of all, let's consider the case of structural data, like MRI data, but also other kinds of data like PET data and many other kinds, which are characterized by the fact that we have one value per subject per brain region. So typically we will have a lot of brain regions, and so this data are characterized by the fact that they have a single value per subject per brain region. So we have a series of brain regions, each one with a certain value. Think of cortical thickness, for example. And the question is, what's the strength of the connection between two given brain regions? How strong is this connection? So when we acquire, for example, MRI, structural MRI data, what we have for each brain region, each column here, and for each subject, each row here, we have one value. Again, think of cortical thickness, for example. And in order to calculate the strength of this connection between these two regions, what we can do is to calculate the correlation coefficients. So we take the brain region A, brain region B, and we plot the values, and then we calculate the correlation coefficient between these. Notice that this is a correlation at group level. This means we get the strength of the connection for one group, not for each subject. And this correlation coefficient, rho AB, obviously by construction we have that rho AB is equal to rho BA, so the connection is naturally bidirectional. What does it mean in terms of matrices? In terms of adjacency matrices? Well, it means that this is a weighted, undirected adjacency matrix. And by the way, we also can see that the correlation of A with A is always 1, therefore the correlation of A with A is 1, and this will be the diagonal. This will tell us that the strength of the correlation, well, the strength of connection of each region with itself will be 1. What we practically do is to ignore the diagonal in the adjacency matrix or the self-connection and cancel all self-connections, or equivalently set the diagonal to 0. So we end up with a weighted connection matrices. So we end up with a weighted, undirected adjacency matrix, which looks like this one. Notice that we have set the diagonal to 0, by the way. And this will have a lot of weights, which since their correlation coefficient go from -1 to 1, and they form an histogram like this one. Now, if we want to analyze, we can analyze this matrix, but it's a very complex one to analyze because it's weighted. What we can do, what we often do in the analysis, is to threshold it to transform into a binary matrix. So the thresholding works like this. So we have this weighted connection matrix with this histogram, and we choose a certain threshold, for example 0.80, which gives us a corresponding binary correlation matrix and corresponding graph. You see that in this case it's very sparse, but we can use a different threshold, for example 0.60, and then we will get something that is less sparse, or 0.40, then we get something that is even more connected. You see, you can choose a threshold, and depending on the threshold you will get a slightly different graph. Then of course the question is, what is the optimal threshold? Well, that's an open question, and we can discuss that in the questions if you're interested in the topic. Okay, so let's now move to another kind of data that is often acquired, which is functional data. This is, for example, data that you might acquire with a resting state fMRI or with EEG and other kind of acquisition of data. In this case, you have a time trace, a time function for each region of each subject. So in this case, the question of how strong is the connection between two brain regions can be answered at the level of a single subject. Again, we acquire the functional data, and which gives us a series of values for each brain region for each subject, typically a time sequence. And then we can calculate the correlation coefficient for each subject, because we have a time sequence for the two regions, so we can calculate the correlation coefficient. And this will give us a weighted correlation matrix for each subject. Once we have the weighted correlation matrix, well, we can use it like we did in the previous case, but we have one for each subject, not one for each group. So we can do more things, more comparisons. Okay, now that we have seen how we can construct the connectivity matrices that we need to make to represent the graph, the question is, what can we do with these graphs? Well, what we can do is to calculate some measures on these graphs. There are plenty of graph measures which represent different kinds of properties of the graph. Here I will give you some examples, very simple examples. Well, the first thing you can think of, given a brain graph, you might want to calculate the degree of each region. What is the degree? It's nothing else than the number of regions with which this region is connected. For example, this region here will have a very high degree. Why? Because it's connected with a lot of regions. this region here will have a low degree because it's connected only to one region. And of course, once you have the degree for each region, you might average the degree, calculate the average degree over the whole network, and then you end up with an average degree. This is a measure for the whole brain. Another kind of measure, which is very interesting, is the path length. What is the path length? The path length is a measure between two nodes. So let's say you take this node or brain region and this node or brain region. So the path length between these two nodes is the distance between the two nodes. Distance in number of edges. So the question is, what is the minimal number of edges to go from this node to this node? In this case, 3. Again, you can in principle calculate the path length for each node, and for each node, and then you can take an average and calculate the characteristic path length of the whole network, averaging the path length of each node. One problem that arises with the path length, you can imagine that, is if two nodes are not connected at all. So if you have a node that is not connected with another node, so it's not possible to go within the network from one node to another, then the path length becomes infinite. That's not good. You can see why, because as soon as you have an infinite and you take an average, the average will also be infinite. So that's not convenient. That's why often, instead of path length, scientists work with the global efficiency. What is the global efficiency? Somehow it's the inverse of the path length. So the global efficiency is 1 over the path length. The good thing of global efficiency is that if your two nodes are not connected, 1 over infinite is equal to 0, so we'll give you 0 instead of infinite. This practically means that you have a 0, which you can nicely average with other values, and that's why global efficiency is pretty convenient from the computational point of view. Again, you can calculate a global graph global efficiency, which is a global measure, which is the average of the global efficiency of each node, which is always well defined, differently from path length, even for disconnected graphs. Another measure that is often encountered, and it's very important, is the clustering coefficient. What is the clustering coefficient? Well, the clustering coefficient answers the question, how well well, take one node, like this one, and the question is the following. Look at all nodes that are connected to this node. The question that the clustering coefficients answer is, how well connected are the nodes that are connected to this node between themselves? Just to give you a different example, not from brain connectivity. The question will be, think of yourself and your friends. The question of the clustering coefficient will be, how well connected are your friends between each other? Are your friends also friends between each other, or they are only friends with you and they don't know each other? So if they're also friends with each other, you will have a high clustering coefficient. If they are only friends with you, then you have a low clustering coefficient. So here in this case, for example, you have this node, which is connected with 3 nodes. In principle, these 3 nodes could have 3 connections, but in reality, they only have 1. Therefore, you have a 33% clustering coefficient. Here you can see another node, this one, which is connected to 2 nodes, which in principle could have a connection between them. They don't have it, and therefore you have a 0% clustering coefficient. Another concept that is often used is the concept of hubs. An hub is a node which is important in the network. How do you define importance? Well, one way is to look at nodes that have high degree. So the higher degree, the more important. If you have a lot of connections, you are important. But you can also think about connector hubs, which are not necessarily with a high degree. In this case, for example, you can look at these nodes here, highlighted here. Well, they don't have very high degree. They have just degree 2. These 2 nodes and these 2 nodes, but they connect the 2 hemispheres. So they are connector hubs, which means that they are important because if you eliminate them, you lose the connection between 2 parts of the network. So the definition of hub depends on what you want to look at. But in any case, an hub in a network is something that it's a node that is important for the functioning and for the structure of the network. Okay, so let's go to one more step, introduce the concept of small worldness. So we can think of graphs that are regular, like this one. You see, it's a very regular graph. Why? Because each node is connected to the two adjacent nodes and to the one after. You see, this node is connected with this one, and with this one, and with this one, and with this one, and same for all of them. It's a very, very regular graph. This is a random graph where each node is connected with random other nodes in the network. A small world graph is something in between them. So you start from the regular graph and you rewire some nodes at random, and you get something that is in between a regular graph and a random graph. Why is this interesting? Well, essentially because when you go from a regular to a random graph, you increase the randomness, this parameter randomness p, from 0 to 1. And as you increase the randomness, what happens to the path length? Well, the path length in a regular graph is very long. And this means that you start from a very high path length. Why? Because, well, if you want to go from here to here, you have to pass through a lot of nodes. In a random graph, the path length on the other end is very small. Why? Well, because you want to go from here to here, you can very quickly go because you have these connections that cross across the path, across the graph, sorry. On the other hand, the clustering coefficient is very high for a regular graph. Why? Well, because each node is connected to all the neighbors, and therefore also the neighbors are connected with each other, so you have a very, very tight community at a local level. But a random graph has a very low clustering coefficient, because if a node is randomly connected with two other nodes, chances are that these two nodes will not be connected with each other. So you see that the random graph has a very low clustering coefficient. What is the problem? The problem is that most networks in real life have both small path length and high clustering. So they cannot be regular networks or random networks. Well, they are typically small world networks, something in between. And the nice thing here is that as you go from a regular network to a random network, the characteristic path length goes down very, very quickly as soon as you rewire a few connections. Why? Because you create shortcuts. Just to give you an example, if you become friends with someone in the US, you create a shortcut between Sweden and the US, and all your friends get a very short path length to all the friends of your friends in the US. You see, you need a very few shortcuts to decrease dramatically the path length, but this doesn't change the clustering coefficient too much. If you have a friend in the US and one in China, likely they don't know each other. But this doesn't really decrease a lot your clustering coefficient if all your friends in Sweden are friends with each other. That's why the clustering coefficient doesn't go down very fast. So this is a very nice way to construct a network that looks like, has the property of real networks, which are high clustering coefficient and small characteristic path length. Okay, finally, now we can construct the graphs, we can calculate some measures, and the next question is, how do we compare two different groups? So if you have a group of healthy subjects and a group of subjects with a disease, how do we compare if the graph measure change between the two groups? Well, what you do typically is this. You have a group of healthy controls and a group of patients. So you can calculate the measure for the healthy control and for the patients. Then you calculate the difference between these two measures. For example, think of the degree. Maybe the healthy control have a high degree, so lots of connections, and the patients have a low degree, so not so many connections. Then you have a certain value for this measure, which means that the difference between healthy control and patients tells us that healthy controls have more connections. The question is this significant? Is this a significant difference? Well, we don't know. So what we can do is to use a permutation test where we remix the two groups, you see, like this, and we recalculate the measures for the new mixed groups, calculate the average, and obtain a certain value. And we do this many, many times, typically 10,000. Let's say 1,000 would be the very minimum. More often you do it 10,000 times, and you end up with an histogram. So when you mix patients and controls, you have a histogram like this one. And at this point, you can ask yourself, what are the chances that by mixing patients as control at random, we get a difference which is higher than the difference we have observed? Well, in this case, it's not very likely, which tells us that in this case, the p-value is 0.01, so we can answer that this is significant. How do we calculate the p-value? It's essentially the probability that you have, by mixing randomly patients and control, a higher difference than in the original healthy control versus patient groups. So in this case, we have a high difference. We could have a different situation in which we have a broader distribution, such as this one, where we have a lot of cases in which by mixing patients and controls, we get higher differences than in the original two groups. In this case, the answer to the question, is this significant, will be no. Okay, so I tried to give you a very, very quick and brief introduction to graph theory concepts to apply to brain connectivity. I first of all explain a bit of history where the concept of graph theory comes from, and it goes back to Euler. Then I showed how one can construct brain connectivity graphs, starting from structural and functional data, obtaining in one case some connectivity graphs at the level of groups of patients, and in the second case at the level of individual patients. Finally, I showed how we can calculate graph measures once we have these connectivity matrices. And at the very end, I showed how we can perform group comparison using a permutation test, which permit us to then tell if we observe significant differences between two groups of subjects. Well, thank you very much, and I will be happy to answer your questions now.